In this video, I will demonstrate how to create a multiple linear regression model using Excel. So we have a new data set for the tracking company that contains 300 observations. Each observation contains the number of miles driven and the number of deliveries, also the driving time. So the driving time will be our dependent variable, or y, and we have two independent variables, the miles and deliveries. Under the data, we're gonna select data analysis, and in that we're gonna select regression. Click OK. So in the y input range, we're gonna select the D column, that is our dependent variable. And in our input Y range, we're gonna select our miles and deliveries column. And then we gonna check the labels because our first row contains the labels or the column names. And we're gonna keep the default confidence level of 95%. For the output range, I'm just gonna output it in the same worksheet over here. And I'm gonna output the residuals and residual plots, and then click OK. So here we have the results of the multiple linear regression. So we can first see that our R-square has improved, right? So R-square now has become 81% compared to the single linear regression. Of course, it's a different data set, but that was 66%. First 10 assignments should be still the same. So we can say that the R-square has improved. So next we can output a equation for this multiple linear regression because we have the coefficients here. In the coefficients, we have intercept, and we have coefficient for the miles and coefficient for the deliveries. So then we can output a equation for this multiple linear regression. Y equals to intersect 0.127337 plus the coefficient for miles 0.067182 multiplied by miles plus 0.689998 multiplied by deliveries, and the y would be the driving time. So that's our equation for the multiple linear regression model. And so what does that mean is that for each single unit of miles increase, and the delivery time will increase by 0.067182 hours. So that should be how many minutes? Let's take a look. 60 minutes per hour. So that's about 4 minutes. That's about the same as compared to the simple linear regression, which is 0.0678. This one is 0.6718. So it's about the same. And for the deliveries, we can interpret such as for each additional delivery made, and the time of delivery would increase by 0.689998 hours. So that would be multiplied by 60 minutes per hour. That would be about 41 minutes. Okay, so maybe that involves like load and unload kind of time. We can also see that the p-value for miles and deliveries, for the intercept, it doesn't matter that much, but you want to look at the p-value for the independent variables, miles and deliveries. Again, p-value tells you whether the independent variables matters. So that is to say whether the independent variable is a significant predictor of y. So we typically look for a p-value that is smaller, the better. And at 95% confidence level, we're looking for a p-value that is less than 0.05. So if our confidence level is 95%, then we're looking at a p-value that is less than 0.05, then we call it statistically significant. So if I 99%, then 1 minus 0.99, that is 1%. So we're looking for a p-value that's less than 0.01. And so then we will say that it's statistically significant. And typically we use at the 95% confidence and a p-value less than 0.05. And we can see that these two p-value actually, both of them are less than 0.05 and also less than 0.01. That is because they're expressed in the scientific format. So you can see the E here. So what that means is that it's actually equals to 3.45 multiplied by 10 to the negative power of 83. So in other words, it's like 3.54 and then multiplied by 0.00000, 83 such zeros. And so this is a very, very small number. So we use the scientific notation using an E that stands for 10 to the power of a negative number. So similar, this is also a very small number. So this means that both miles and deliveries are a significant predictor for the time of delivery. So we can also see that the residual plots and delivery residual plot, they're randomly distributed along the means of 0. So this shows that the multiple linear regression model has good invariance. So it's good for predicting the time of delivery. And because residual equals to actual y minus predicted y, so if we have a positive residual, that means actual is greater than predicted value of y. So it means that the model underestimated. If we have a negative residual, that means actual is less than predicted value of y. So that means the model overestimated. And we want to see a good balance of the overestimate and underestimate to see most of the data are like around the means of 0. And the fact that we are seeing the data laying the strikes like this is because the nature of the data. Deliveries is ranging from 1 to 6, and there's no such number of deliveries of 1.5. So therefore you don't see any data between 1 and 2, 2 and 3, and so on. And so this is entirely normal, and we don't say that the residual has a pattern, even though you're seeing the stripes, and that's just the nature of the data. And similarly, the miles ranging from 40 miles to 100 miles, and because they're like in 5 increments, so 40, 45, 50, 55, there's no number of miles that's like 42, 43, etc. That's why you're seeing the residuals data look like, again, stripes. So lastly, we can create a scatter plot of the predicted value and residual. So we have the predicted time and residual in here. We can just create a scatter plot. So highlight them and then insert a chart that is scatter plot. And we can see that the residuals again are randomly distributed along the mean of 0. So there's no obvious pattern, which is really good. We don't want to see a pattern of the residuals, and we want to see them randomly distributed, and they're kind of evenly along the line of means of 0. So this means that this linear regression model has good intervariance and can create pretty good predictions.